Welcome back. In this video, we're going to work on factoring the difference of two squares. This is another one of our factoring patterns. Again, recall your multiplication patterns. Recall that when we had the pattern a plus b times the quantity a minus b, when we multiplied that together, that gave us a squared minus b squared. Because when we checked that linear term, of course, we had a plus ab and a minus ab, and that linear term dropped out. Well, we know that factoring is the reverse of multiplication. So we know that 8, or 2 cubed times 3, when we multiply that together, we get 24. So by multiplication, 8 times 3 is 24. Well, the reverse of that, 24, split into its factors, is 2 cubed times 3. That's by factoring. So if we can reverse multiplication and find factors, we can also reverse our multiplication patterns. So that must mean then that a squared minus b squared, when factored, gives us the pair of binomial factors a plus b times the quantity a minus b. So this will be a good pattern to memorize. You already have memorized it for multiplication, and now we need to reinforce that and do that in the opposite direction for factoring. It will be helpful for you to know and recognize your perfect squares. A perfect square is the result of any mathematical expression that's raised to the second power. So any quantity squared, like a squared and b squared, are perfect squares. In fact, anything raised to an even exponent, okay, is a perfect square. So even if it was to the 4th power or to the 6th power, to the 8th power, any even exponent is going to be a perfect square. I suggest you write that in your notes, even though I haven't written it here. So we can take the square root of these, or even these binomials down here, very easily and get the square root of a squared is a, and the square root of b squared is b. Okay? The square root of x plus y quantity squared is x plus y. The square root of x minus 4 quantity squared is x minus 4. The square root of 3x minus 4y squared is 3x minus 4y. And just to give you an example, the square root of x to the 4th is x squared. Okay? Because, well, what's x squared times x squared? Same number multiplied 2 times in a row. There you go, is x to the 4th. Okay? And that works for any even exponent. So the easiest perfect squares are numbers that we can take the square root of and get the integer for the answer. Okay? You guys are going to need to memorize and know your perfect squares. So, for example, 1 squared, well, 1 times 1 is 1, and the square root of 1 is also 1. That makes 1 a perfect square, probably the most commonly forgotten perfect square. 2 squared is 4, and the square root of 4 is 2, making 4 a perfect square. And the pattern continues. 3 squared is 9. The square root of 9 is 3. 4 squared is 16. Square root of 16 is 4. 5 squared is 25. And the square root of 25 is 5. So our perfect squares are all these numbers that I have circled. And we will keep going. I'm going to hold you to knowing and memorizing all these perfect squares. 6 squared is 36. 7 squared is 49. 8 squared is 64. 9 squared, 81. 10 squared is 100. So you'll need to know that the square root of 36 is 6. The square root of 49 is 7. The square root of 64 is 8. Because this is some quantity squared, we're going to want to undo that. So again, I'm going to hold you for recognizing these perfect squares. And I'm going to continue. 11 squared, 12 squared, 13 squared, 14 squared, 15 squared. So my perfect squares here, 121, 144, 169, 196, and 225. You'll also need to know some simpler ones. 20 squared. Well, 20 times 20 is 400. We know 2 times 2 is 4. We know 10 times 10 is 100. 25 squared, a little tougher. That is 625. So the square root of 625 is 25. 30 squared is 900. 40 squared is 1600. And so on. So those are some perfect squares you should know and recognize. Now we'll move on to our samples. So using our pattern that x squared or a squared minus b squared factors to a plus b times a minus b, let's factor the binomial 25x squared minus 1. We've got a perfect square and 25x squared. We can easily take the square root of that. Difference, it's a minus sign, and 1 is a perfect square. So this is a difference of two perfect squares. So the square root of 25x squared is 5x and 5x, and then the square root of 1 is 1, so 1 is plus, 1 is minus, and we have factored that using our pattern for the difference of two squares. X squared minus 9/16. Well, that is a fraction, that's true, but 9/16, I've got a perfect square in the numerator and a perfect square in the denominator. So I'm going to factor that x and x. It's a difference of two perfect squares, so 1 is plus, 1 is minus. And then 9/16, well, we can take the square root of each of those. So x plus 3/4 and x minus 3/4. X to the 4th minus y to the 14th. Well, 4 is a perfect square, and because this is an exponent, 14 is a perfect square, right? X squared times x squared is x to the 4th, is x to the 4th. So that's going to factor x squared and x squared. And believe it or not, y to the 14th, well, is y to the 7th times y to the 7th. So we can do plus y to the 7th and minus y to the 7th. And if you don't believe me, go ahead and refoil it. And sure enough, we get x to the 4th, y to the 7th times y to the 7th is y to the 14th. And our linear term, because we have a positive x squared y to the 7th and a negative x squared y to the 7th, when we check our smile, that drops out. And a minus x squared y to the 7th. So, sure enough, we have factored that correctly. X to the 4th minus 256. I didn't give you that one in one of our patterns, but 256, the square root of that is 16. So we get x squared plus 16 and x squared minus 16. Now this one is a little sneaky because I have a sum of two perfect squares. X squared and 16 are perfect squares. That's not factorable. So that would just stay x squared plus 16. But x squared minus 16, this binomial is still factorable. Pretty tricky. So we have a square root of x squared is x and x. And sure enough, this is a difference of two perfect squares. So that can be factored further to x plus 4 times x minus 4. So this x squared minus 16 we could still factor. So our three factors are x squared plus 16 times x plus 4 times x minus 4. X squared plus 9, it looks like a difference of two squares. Unfortunately, it is not a difference. We've got a plus here. So this is not factorable. That's what we saw in that last sample problem. So that's not factorable. 9x cubed minus 25x, it looks like a difference of two squares. 9 is a perfect square, 25 is a perfect square. But we can't take the square root of x and we can't take the square root of x cubed. However, our first rule of factoring is to take out the GCF. And our greatest common factor here is x. So we factor out the x and we're left with 9x squared minus 25. Well, now 9x squared is a perfect square and 25 is a perfect square, so that continues to be factored, and it's a difference of two squares that can be factored. 3x plus 5 times 3x minus 5. So our factors are x, 3x plus 5, and 3x minus 5. 48x to the fourth minus 3. 3 is not a perfect square. 48 is not a perfect square. X to the fourth is. And what we have here is two terms that I can factor out a 3. So if I factor out a 3, I'm left with 16x to the fourth minus 1. And 16x to the fourth is a difference of two squares. So I bring down my 3, and that's going to factor 4x squared plus 1 and 4x squared minus 1. And sure enough, this is a perfect square and a perfect square, but it's a sum. But this factor here is a difference minus of two perfect squares, so that can be factored some more, somewhat like our previous sample problem. So we get 4x squared plus 1, and then we can still factor this to 2x plus 1 times 2x minus 1. So 48x to the fourth minus 3 can be factored all the way down to 3 times 4x squared plus 1 times 2x plus 1 times 2x minus 1. And if you boil this all together, you would get 48x fourth minus 3. Negative 25x squared plus 121. I never really like negative x squareds, so I'm going to factor out a negative 1. So I get the opposite of 25x squared. Clean that up a little bit for you. Becomes the opposite of 25x squared minus 121. And sure enough, this binomial is a difference of two squares. So I have to carry down my negative sign, and it's 5x plus 11 and 5x minus 11. And so that's fully factored, the opposite of 5x plus 11 times 5x minus 11. Leave that negative sign there, you're going to need it. And our final sample problem, x squared minus y plus 3 quantity squared. Well, this is a difference of two perfect squares. Anything quantity squared is a perfect square. So this can be factored into x and x. And of course we know one is going to be plus and one's going to be minus. So this is like my a, and y plus 3 is kind of my b squared. So it's x plus y plus 3 and x minus y plus 3. Right? X minus b times, or x plus b times x minus b. But we can continue to simplify. So this is just x plus y plus 3. But this particular binomial, we have to impose the opposite of both. That's our fraught with peril. So that becomes x minus y minus 3. So our fully factored is the trinomial x plus y plus 3 times x minus y minus 3. So something a little more challenging on the end. We'll see some more of those in class. So that is your difference of two squares patterns, and we will see you in class.